2.5 is about extrema. We're going to talk about relative extrema, which in previous classes you might have referred to as a local max or a local min. We're going to talk about absolute extrema, which means exactly what it sounds like, the absolute highest or lowest value of a y value in a function. And we're going to talk about how to determine those extrema. So relative extrema, again, you may have referred to them in previous classes as local max and mins, are points where the function has the largest or smallest values in a given neighborhood. So for example, I'm going to just sketch a function off to the side. If I had a function that looked something like this, there are multiple local maximums along that function, as well as there are multiple local minimums along that function. So local or relative extrema, meaning they are extreme given what is happening to the left and the right of those values. And what we're going to focus on today is how you can use the first derivative of a function to identify if you have a local max or a local min. Something important to note, because this says in a given neighborhood, meaning what's happening around it on both sides, this cannot include endpoints. Cannot include endpoints. So if we're talking about a closed interval, we are not, the endpoints cannot be a relative max or a relative min. Absolute extrema exists when there are points that have the largest or smallest y value over the entire function. In calculus, we're only going to consider them over a closed interval. So we could say, on the interval from 0 to 5, what is the absolute maximum and absolute minimum? And we're talking about y values of the function on that interval. Because of that definition, these can include endpoints. So relative extrema, absolute extrema. Let's look at a couple examples, just sketching. So this first example says, sketch a graph with the following criteria using a closed interval. A function that is continuous and has a change in behavior from increasing to decreasing at x equals 1. So x equals 1 is right here on my graph. So it's increasing when it hits x equals 1, it's decreasing. And let's just give this some endpoints here because it says it's a closed interval. So looking at this graph, down here, this value is the absolute minimum value of the function. It is the lowest of any points in the interval that we're considering. This point here is the absolute maximum. It also is a relative max because it's not an endpoint and it is still a maximum value. Relative meaning to the left and the right, this is still a maximum. This other endpoint is neither a relative nor an absolute max or min. It can't be relative because it's an endpoint, and it's definitely not the absolute highest or lowest y value in the function, so it just is basically nothing. It's just an endpoint. The second example says a function that is continuous and has a change in behavior from decreasing to increasing at x equals 1. Again, this is a closed interval. So we can look at this again. Here we're going to have not only a relative min, but also an absolute min. Here we're going to have an absolute max. So if you're looking at a graph or a piece of a graph, you're really just identifying the highs and lows, the peaks of the function over the interval that we're considering. But how do we mathematically identify extrema? That's what we're going to focus on in the rest of this section. So the first thing to think about is what's actually happening at an extrema. This function is increasing, then it hits the extrema and it starts decreasing. Or this function is decreasing, it hits the extrema and it starts increasing. So extrema occur at a change in behavior of the function. What would be happening on f of x that would describe this change in behavior? Think about what's happening. It's getting bigger and bigger and bigger, and then it's getting smaller and smaller and smaller. What is changing? That is the slope. The slope is changing from positive to negative or the other way around. Second thing to consider, does a function have to be differentiable at a relative max or min? Can you give an example? So can you think of a function that has a max or a relative max or min that is not differentiable at that value? So for me, the first thing that comes to mind is absolute value. So f of x equals the absolute value of x is a counterexample here. This is not differentiable at x equals 0. It's a sharp turn. But x equals 0, or the point 0, 0, is definitely a relative and absolute minimum of the function. So does the function have to be differentiable to have a relative max or min? No, it does not. And then the last thing to consider before we formalize this is to determine the candidates for extrema, we need to take into account what we call critical numbers. And this is a big concept. You're going to see this very commonly abbreviated as CN or CNS. Critical numbers are x values that are defined in the original function. This is a really big deal. They are defined in the original function, and we're looking at where the derivative is 0 or where the derivative is undefined. So when we think through critical numbers, one thing is to consider is you need to first identify all of the domain restrictions in the original function. Those will not be possible values or candidates for critical numbers. So the first derivative test is something that enables us to identify these relative maxes and mins. And here's how it works. When you start a problem and you're being asked to find the relative extrema, you first need to identify if there are any domain restrictions at the beginning of the problem. If there are any domain restrictions, you need to keep those in mind solely because those cannot be critical numbers. So identify any domain restrictions. The second thing you need to do is find the derivative and set the derivative equal to 0. You're going to look for where the derivative is 0 and where the derivative is undefined. Those are the values, that's what step 2 is talking about. Those are the values that are going to give you your critical numbers. Where the derivative is 0 and where the derivative is undefined. Then you're going to create a number line, a positive, negative, or a sign chart, if you will, for those critical numbers, and you're going to test the values in the derivative to figure out where the sign is changing. You can use that to identify if you have relative maxes and mins. So something really important to note, and I have seen this so many times on AP tests, on practice problems, when you are making a sign chart, that is not enough of a justification. You can't just draw a sign chart and then draw a conclusion. When you're taking an AP test, and even when you're taking a test in my class, I'm not allowed to grade that as your justification. You need to justify in words what that sign chart is saying. So I'm going to really hit that hard when we start working through these examples, but just make sure that you are doing those things. So I'm going to add a couple tips next to these bullet points or these numerical values steps here. Okay, let's work through some examples and really focus on each of these steps while we work through this. So we are given a function to the power of 2/3. So the first thing I'm asking myself is, are there any domain restrictions in the original function? And there are not. And you don't have to note this, but I'm just going to note it for myself. There are no domain restrictions. The next thing I'm going to do is I'm going to find the derivative. So f prime of x, we're going to use the chain rule here, is going to be 2/3 times x squared minus 9 to the negative 1/3 power times the derivative of the inside, which is 2x. So thinking about this, we do have domain restrictions here. X squared minus 9 to the power of negative 1/3 is going to be in the denominator, and the denominator can't be 0. So we have two domain restrictions, and those are plus or minus 3. X can't be plus or minus 3 in the derivative. So those are going to be things we need to consider when we look for critical numbers. So we're going to set that derivative equal to 0. So 0 equals 2 times 2 is 4. 4x over x squared minus 9 to the power of 1/3. So then I'm just asking myself, what makes the numerator 0? The numerator is 0 if x is equal to 0. So we can go ahead and identify based on this. So therefore, our critical numbers are 0 and plus or minus 3. Now being a critical number does not necessarily mean that there's a local max or a relative max or min at any of these three values. In order to check, we need to look at the sign chart. So I'm going to go ahead and draw a number line. I'm going to put these three values on there, -3, 0, and 3. And I'm going to make a note to myself off to the right-hand side that this is the first derivative sign chart. Sometimes I forget when I'm making multiple sign charts on a problem which one is which, and I find it really helpful to label it just right next to the number line. So if I plug in a number into f prime that is less than -3, like -4, thinking about what's happening in the denominator, that's going to be positive. The numerator is going to be negative, so this is going to have a negative value. If I plug in a number between -3 and 0, so like -1, the denominator is going to be negative, and the numerator is going to be negative, so that's going to give me a positive value. Between 0 and 3, if I plug in, say, 1, I'm going to have a positive number in the numerator and a negative number in the denominator. And then if I plug in something greater than 3, like 4, positive both in the numerator and the denominator. So here's my sign chart. I like to just, this helps me understand what I'm talking about. This function is decreasing, and then it starts increasing. So right there, looking at that graph, that's showing me that there is a relative extrema here. There's a relative min. Then it's going from increasing to decreasing, another relative extrema, from decreasing to increasing. So we just identified that each of these three numbers happens to be a relative max or min. Remember, you have to justify in words what this relative extrema is. You can't just have your sign chart be your evidence. So what I'm going to do is I'm going to say that there is a relative min at x equals -3 because the sign of f prime changes from negative to positive, or because the derivative is going from decreasing to increasing at that value. Similarly, we can say that there's a relative maximum at x equals 0 since f prime changes from positive to negative. So this right here absolutely must be said as a justification for what you did. If you have the sign chart and then you just say there are relative mins at these values, that is not enough of a justification. This problem says ordered pairs, so I'm just going to add those off to the side. There's not a ton of room, but I'm going to create some space right here and add these. So there are relative mins at -3, 0 and +3, 0. So let's just say plus or minus 3, 0. And there's a relative max at 0, -9 to the power of 2/3. Typically, you're just going to be asked for the x values. You're not going to be asked for the ordered pairs. And then it asks us for the intervals in which this is increasing or decreasing. It is increasing from -3 to 0 and from 3 to infinity. It's decreasing from -infinity to -3 and 0 to 3. I just really don't have space to try and fit that in there. So increasing -3 to 0 and 3 to infinity, decreasing -infinity to -3 and 0 to 3. So let's recap what we did. We identified any domain restrictions. We found the derivative. We found where the derivative was either 0 or undefined. Those are our critical numbers. We created a sign chart for the derivative at those critical values or critical numbers. And then we used that sign chart to figure out how the sign was changing for the derivative to identify if there were relative maxes or mins. Let's follow that same process for 1, 2, and 3. So if you want to pause this video and try that, and then unpause it and see how you did, that's a great idea. So number 1 is a polynomial. That means there are really no domain restrictions at the beginning of this problem. So the next thing I'm going to do is find the derivative. F prime of x is going to be 3x squared minus 6x. Plus 3. That is defined everywhere. So I'm going to set that equal to 0. I'm going to divide by 3 also. So x squared minus x minus 2x plus 1. This factors and solves to just be x equals 1. So this is our one and only critical number. So we're going to make a sign chart with only that number on it. If I plug in 0 to the derivative, I get 1. That's positive. If I plug in 2 to the derivative, I'm going to get also 1, which is also positive. So this is not changing sign at all. The derivative is positive throughout the entire function, with the exception of at 1 where the function is equal to 0 or the derivative is equal to 0. This means there are no relative max or mins on this function. So that's something that's really important to note. Not every critical number is going to be an extrema, and not every function is going to have necessarily an extrema. So those are just really important things to note. We had critical numbers, they were not extrema. This function is increasing everywhere since the derivative is positive everywhere, so it's increasing from negative infinity to infinity. It's not decreasing anywhere, or it's increasing on all real numbers. Number 2, we do have a domain restriction at the beginning of this problem. X is not allowed to be 0. Otherwise, the denominator would be 0. And I'm actually going to rewrite this as a function that will be much easier to integrate. If I split this, I get x to the 4th over 3x, which is the same thing as x to the 3rd over 3, plus 3 over 3x, which simplifies to be 1 over x. Now let's go ahead and take the derivative. G prime of x is going to be 3x squared over 3, or just x squared, minus 1 over x squared. Now looking at this function, I want to identify where this is undefined or 0. Well, it's undefined at x equals 0, but that was a domain restriction. So I'm not allowed, that's not on my list of possible critical numbers. So I just want to see where this is going to be equal to 0. And if I solve that out, I'm going to get that x is equal to plus or minus 1. These are my only critical numbers. So I'm going to make a sign chart with -1 and +1. This is my f prime sign chart. If I plug in a number like -2, that's going to give me a positive number. Also, I think you don't have to include this on your sign chart, but it is important to note that this function is not defined at 0, so it is important to think about what's happening between -1 and 0 and what's happening between 0 and 1. For this particular function, all of those values are negative. If you plug in -1/2 or +1/2, no matter what there, you're going to end up with a negative number. And then if I plug in something along the lines of 2, I'm going to end up with a positive number. So here, the function is going from increasing to decreasing. Here it's going from decreasing to increasing. So we are going to have both a relative max and a relative min. Remember, you have to justify how you know that without using your sign chart. You need to have a sentence or words explaining there is a relative max at x equals -1 because the derivative is changing from positive to negative there. There is a relative minimum at x equals 1 because the derivative is changing from negative to positive. You have to have that written down. So make sure that you mention all of those things, and I just typed that all in red down at the bottom. So this function is increasing from -infinity to -1 and from 1 to infinity. We know this because f prime is positive. Again, you have to state that justification. You have to identify why you know that. We know that it's decreasing from -1 to 0 and from 0 to 1 because f prime is negative. You do have to separate those two intervals because or I guess I should say g for all of these, g is not defined at 0. So let's just change these all to g's. G prime. Okay, so go ahead and pause the video and then work through number 3. I'm going to do a little erasing here so you can see my work on number 3. Okay, there are no domain restrictions on h of x. H prime of x is going to be 1 minus 2 cosine of x. We're looking at the interval from 0 to 2 pi. So we're looking for where 0 is 1 minus 2 cosine x, or where cosine of x is equal to -1/2, +1/2. That's going to give us that our critical numbers are pi over 3 and 5 pi over 3. So now we're going to make our sign chart. We're going to label that h prime for our sign chart, pi over 3, 5 pi over 3. That looks like negative, positive, negative. So that's going to give us a relative min and a relative max. Again, we need to write that out fully. So I'm going to go ahead and type that down. We're going to have a relative min at pi over 3 because the derivative goes from negative to positive or decreasing to increasing. we're going to have a relative max at 5 pi over 3 because the derivative goes from positive to negative. And then again, I'm out of space, but if we were stating where the function is increasing, it's increasing from pi over 3 to 5 pi over 3 because the derivative is positive, and it's decreasing from 0 to pi over 3 and 5 pi over 3 to 2 pi because the derivative is negative. So that's the first derivative test. That's the process you're going to go through when you're looking for relative maxes and mins. We introduced the idea of an absolute max or min, but now let's look at how we can identify if something is an absolute extrema. In order to talk about absolute extrema, we're going to be looking over a closed interval, and we're going to extend the candidate test to include the endpoints as well as the critical numbers. So we're going to do a lot of the same things that we just did, but we're also going to test the endpoints. That's the big difference. We're going to test the endpoints of the interval as possible critical numbers. So you're going to start again by identifying the domain restrictions in the original function, finding the derivative and figuring out where that derivative is 0 or undefined, doing a number line to check, and testing for the sign in each interval of the derivative. Then you're going to test all of those candidates from the critical numbers as well as the endpoints themselves. So I have actually seen on a lot of AP released questions and scoring guides that they're really looking for you to identify all of those possible candidates and show that you checked or justified why they could or could not be candidates. So let's look at this first example. Use the candidate test to determine the absolute extrema over the function from -1 to 3. So right now you should already know you're going to have to check -1 and -3 as candidates. But let's go through that process to see if there are any other values we need to check. So the function is continuous everywhere. There's no domain restrictions. So the next thing we need to do is look at the derivative. So let's take the derivative. 3 times 1/3 x squared is just going to become x squared minus 4x. That's defined everywhere. So let's see where it is 0. It's going to be 0 when x is 0 and x is 4. So these are our critical numbers, and we also need to include the endpoints of the interval. And right now you should notice, hey, negative or positive 4 is not actually in this interval, so this is not a candidate. So we're going to make a sign chart for f prime with -1, 0, and 3. Since this is a closed interval, I don't need to check anything below -1. I need to plug in something like -1/2 to get what's happening between -1 and 0. If I plug that in, I'm going to get a positive number. If I plug in +1, I'm going to get a negative number. And those are the only two values I need to check because that interval goes from -1 to 0. So it does look like there could be some relative extrema happening here. So our candidates are still going to be all three numbers. We need to look at what happens when x is -1, what happens when x is 0, and what happens when x is 3. So we're just plugging all three of those numbers into the original function. So -1 gives us 7/3, 0 gives us 0, 3 gives us -9. And then we're literally just identifying what is the biggest number here, 0. That's going to be the absolute maximum of the function is 0, and that happens when x is equal to 0. The absolute minimum of the function is 9, and that happens when x equals 3. And we can say that by the candidate test. So by the candidate test, we're identifying the absolute max and min. Notice I'm identifying the value of the function. I'm not identifying the x value. You need to be cautious at looking for what the question is asking for. The absolute maximum of the function on this interval is 0. The absolute minimum of the function on this interval is -9. So let's wrap up by just looking at a couple more examples. You can pause the video while you work through them on your own and then check your work afterwards, or you can follow along with me. So number 4 gives us an absolute value function, and something important to remember is you can always just split the absolute value function into a piecewise function. So f of x is going to equal, and I guess I should say, this when x is between 0 and 5, and when x is between 2 and 5. Let's rewrite those intervals. That looks better. So this is an absolute value function. Looking at this function, we can just take the derivative by taking the derivative of the pieces. Remember that the original function is defined everywhere. There's no domain restrictions, but you're going to see right away If I take the derivative of this, I'm going to get -1 on this first interval, and I'm going to get +1 on this second interval. So the only place that we might have issues with the derivative is at the value of 2, and we definitely do have an issue at 2 because both pieces of this function don't have the same derivative. I have -1 and +1. So the derivative does not exist when x is equal to 2. And we know that anyways because this is an absolute value. There's a sharp turn at the vertex of the absolute value function. We also need to consider the endpoints, which are 0 and 5. So there's our list of critical numbers. We're going to go ahead and make a sign chart, 0, 2, and 5. Between 0 and 2, this is negative for the derivative. Remember, this is f prime. And between 2 and 5, this is positive. So all three of these are still candidates. So we're going to test each of them, f of 0, f of 2, f of 5. F of 0 is 2, f of 2 is 0, f of 5 is 3. So the absolute max is 3, the absolute min is 0, and we can state that by the candidate test. Okay, let's go ahead and look at number 5. So that is continuous along the interval that we're looking at. We're going to take the derivative. That's going to give us f prime of x is equal to 2 cosine of x plus 2 sine of 2x. There's a little chain rule action happening there. I'm just going to tell you, you can use trig identities to simplify this, but honestly, to save us time, I'm just going to tell you all of the x values where this is true. You could also use a graphing calculator and check, but there are a lot of critical values here. 0, because it's an endpoint of the interval, pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6, and 2 pi. So you can make the sign chart for this. I'm a little bit out of room, but I'm going to make it. What I'm going to do is just take over down here. If we make the sign chart for each of those values and checking this negative, positive, positive, negative, positive. So we actually do have to check every single one of these values, and I'm going to go ahead and do that. So there's all of those values. Now you're looking at all those values and we're identifying the absolute max and the absolute min. The absolute max is 3. The absolute min is -1.5 or -3 over 2, and that is true by the candidate test. Okay, last problem. I apologize. This video got very long, but these are some pretty important concepts. There are no domain restrictions in the original function, so we're going to go ahead and find the derivative. This derivative is undefined when x equals 0. We can set the derivative equal to 0 and find that x is going to equal 1. So our critical numbers are 0, 1, and the endpoints, -1 and 3. So we're going to go ahead and make our number line and then test each of those values. So based on testing those candidates, we're going to find that the absolute max of f is 5 and the absolute min is 0 by the candidate test. So briefly recapping these notes, the first derivative test enables us to identify critical numbers, which helps us identify local extrema, local max and min, or relative max and min. The candidate test adds the endpoints of a closed interval of the function to help us identify absolute max and min of a function over that particular interval. Thanks for listening.